So, good morning students, this is Arvind, Assistant Professor, Department of Physics, DBS, Topology. So, in the previous class, I started the fourth unit, that is static series compensation. So, in that class, I discussed about concept of series compensation and introduction to the architecture of series compensation. And in the same class, I discussed about the voltage stability objective. And now in this class I am going to discuss remaining objectives, that is transient stability improvement, polarization damping, and subsynchronous resonance, like that. Okay. Firstly, I will start with the next objective, that is improvement of transient stability. So this is the another objective of series compensation. Okay. So the transient stability improvement by controlled shunt compensation. Okay, that is, I am discussing about the previous concept. That is static shunt compensation. In that one, what we did means the transient stability improvement by controlled shunt compensation is achieved by increasing the power transmission via increasing the transmission line voltage during the accelerating swing of the distributed machines. Okay, so disturbed machines. Okay, like that we are improving the transient stability. So you know already the what is meant by stability and what is meant by transient stability. So now only I am going to discuss the stability. The stability is the ability of the system to bring it to a normal or stable state after being disturbed. That is called stability. We have three types of stability. Depending upon the magnitude of the disturbance, we have three types of stability. One is steady state stability, and another one is transient stability, and another one is dynamic stability. So in this class, we are going to discuss transient stability. Means what is meant by transient stability first. So the transient stability is the ability of the system to bring it to a normal or stable when there is a large disturbance occurs. So large disturbance means sudden change in the load or switching operations, like that we have this one. So the transient stability improvement by controlled shunt compensation is achieved by increasing the power transmission via increasing the midpoint transmission line voltage during the accelerating swing of the disturbed machine, and the powerful capability of. So now I am discussing this concept of series compensation. So the powerful capability of series line compensation to control the transmitted power can be utilized much more effectively to increase the transient stability limit and provide power oscillation damping. Okay, the powerful capability of series line compensation to control the transmitted power can be utilized much more effectively to increase the transient stability limit and to provide power oscillation damping. So here in the previous concept, that is the shunt compensation, we are using equal array criterion. So the equal array criterion is used to give the maximum capability of power in the system. So the equal array criterion introduced in the shunt compensation. Why? Because to investigate the capability of the ideal shunt compensator to improve the transient stability. So same concept we are used again here to assess the relative increase of the transient stability margin attainable by series capacitive compensation. That means in this concept also we are using the same equilibrium criterion concept to improve the transient stability. Okay, so for that one I am taking the simple system with the series compensated line. So already we discussed this thing, the first diagram I am taking. So this diagram, so actually this diagram is taking for the concept of series compensation also. Same diagram I am taking. So here I am taking two machine power system with series capacitive compensation. So in this one we have the reactor also. We have reactor also. It consists of the value x by 2 and x by 2. It is split into 2. So on the left side and on the right side we have the same components with the same values. Okay. So here it consists of the capacitor and reactor combination. So the capacitor consists of the xc by 2 value and the reactor consists of the x by 2 value. On the right side and left side we have same, and we have on the left side we have sending in voltage, and on the right side we have the receiving in voltage, and in the middle we have the midpoint voltage, and totally we have the current I. So as per the shunt compensated system that is shown in the figure, that is 5.1. So this one, okay, here we are considering that at the midpoint we have the ideal compensator. At that time the power is equal to 0 and we have the midpoint voltage Vm, and the receiving end on the left, on the right we have the receiving end voltage, and on the left side we have the sending end voltage, that is Vs, and we have one reactor both sides, that is it consists of the same as, that is X by 2, and we have the currents, that is ISM and IMR. ISM means the sending end and midpoint voltage, midpoint current, and IMR is the midpoint receiving end current we have. Okay, so as per the shunt compensated system shown in the figure 5.1, that is it is for the convenience, also assumed for the series compensated case, so that the pre-fault and post-fault systems remain the same. Okay, so for the series compensated case, the pre-fault and post-fault systems remains the same. Okay. So suppose that the system of figure, that is A 6.1A with and without series capacitive compensation transmits the same power Pm. Okay. Suppose that the system with and without series capacitive compensation transmits the same power, that is Pm. So assume that both the uncompensated and series compensated systems are subjected to the same fault for the same period of time. So the dynamic behavior of this system is illustrated in the figure, that is 6.3, A and B. So A and B. So the A diagram gives the equilibrium criterion for the transient stability margin for a simple two-machine system, that is for without compensation, and second diagram, that is B diagram, is for the with a series capacitor. Okay, so here the characteristic diagram is drawn between power and delta in both the cases. So in the first case, we are drawing a curve that is drawn between delta is equal to 0 to pi, and in that curve we have the Pm, that is the midpoint voltage, and maximum power. So up to midpoint voltage we have the A1 area, and up to P maximum we have the, from Pm to P maximum we have the A2 area, and finally we have the A margin and power values. Okay, and in the second case we are taking the curve between power versus delta. So here the delta is between 0 to delta circuit, and the power is between Pm to 1.5 P maximum. So here we draw two curves. One curve is drawn for the P maximum, that is represented in the dotted line, and one more curve is drawn for the 1.5 P maximum value, that is 1.5 times of the P maximum in the previous case comparison. So here we have the two areas, that is AS1 and AS2, and we have the margin, that is area margin, that is AS margin, and we have the sending end power, that is equal to V squared by 2x into 1 minus x 1 minus k into sin delta. Here k is equal to 1 by 3. Okay, so here the angle is changes from delta S1 to delta S2, and delta S2 to delta S, and delta S3 to delta S circuit, CRIT, like that. Okay, so as seen prior to the fault, both of them transmit power, that is Pm, at angles delta 1 and delta S1. So comparing the both diagrams, two diagrams A and B, so prior to the fault, that means during the fault, both of them transmit power, that is Pm. Both of them transmit power Pm at angles delta 1 and delta S1 respectively. So in the first curve, it is drawn at delta 1, and in the second curve we draw delta S1. So that one we have the curve, that is A1 and AS1. Okay, so during the fault, the transmitted electric power becomes 0. Okay, during the fault, the transmitted electric power becomes 0, while the mechanical input power to the generator remains constant, that is Pm. So while the mechanical input power to the generator remains constant Pm, that is during the fault condition. Okay. Next, therefore, the sending end generator accelerates from the steady state angles, that is delta 1 and delta S1. Okay. Therefore, the sending end generator accelerates from steady state angles, that is delta 1 and delta S1, to angles delta 2 and delta S2 respectively when the fault clears. So after the fault clearing, that is the post-fault condition, we have the steady state angle changes, that is from delta 1, delta S1 to delta 2, delta S2. Okay, like that it is changing. Okay. Next, the accelerating energies are represented by areas A1 and AS1. So the accelerating areas are represented by areas A1 and AS1 at delta 1, delta S1. So A1 on the first curve, AS1 on the next curve. So these two are the accelerating areas. These two are the accelerating areas on the system. And after fault clearing, the transmitted electric power exceeds the mechanical input power. Okay, after the fault clearing, the transmitted electric power exceeds the mechanical input power, that is more than input power, and therefore the sending end machine decelerates. Okay, so however, the accumulated kinetic energy further increases until a balance between the accelerating and decelerating energies. Okay, the accumulated kinetic energy further increases until a balance between accelerating and decelerating energy is represented by areas, that is A1, AS1 and A2, AS2 respectively. So A1, AS1 is the accelerating areas and A2, AS2 is the decelerating areas. Those are reached at the maximum angular strength, that is delta 3 and delta S3. So he is reached at the maximum angular strength, that is delta 3 and delta S3 respectively. So delta 3 and delta S3 in both the diagrams. So the areas between the P versus delta curve and the constant PM line over the intervals defined by angles delta 3 and delta CRIT and delta S3 and delta CRIT respectively. So the areas between P versus delta curve and the constant PM line over the intervals defined by the angles delta 3, delta S, delta CRIT and delta S3 and delta CRIT respectively. So those determine the margin of transition stability, that is represented by areas, that is A margin and AS margin. So from this diagram, so A margin and AS margin and delta 3, delta S3 and delta CRIT and delta SCRIT. Okay. So comparison of figures, that is 6.3 A and B, clearly shows a substantial increase in the transient stability margin. Substantial increase in the transient stability margin. So the reactive capacitive compensation, the series capacitive compensation can provide by practical cancellation of the series impedance of the transmission line. Okay, the series capacitive compensation can provide by partial cancellation of the series impedance of the transmission line. So the increase of transient stability margin is proportional to the degree of series compensation. Okay, the increase of transient stability margin is proportional to the degree of series compensation. So theoretically, this increase becomes unlimited for an ideal reactive line as the compensation approaches 100%. Okay, theoretically, this increase becomes unlimited for an ideal reactive line as the compensation approaches 100%. So, however, practical series capacitive compensation does not usually exceed 75%. Okay, only ideal reactive line as the compensation approaches 100%. But however, practical series capacitive compensation does not usually exceed 75% for a number of reasons. So those including load balancing with panel pass, high fault current, and the possible difficulties of power flow control. Like that, these are the number of reasons why the practical series capacitive compensation does not exceed 75%. Okay, so often the compensation is limited to less than 30% due to subsynchronous congruence. Okay, often the compensation is limited to less than 30% due to subsynchronous congruence. So it is emphasized here again that under practical fault scenarios, the pre-fault and post-fault systems are generally different. It is emphasized here again that under practical fault scenarios, the pre-fault and post-fault systems are generally different. Okay. So from the standpoint of transient stability and of overall system security, the post-fault system is the one that matters. Okay, from the standpoint of transient stability and of overall system security, the post-fault system is one of the in overall system, the post-fault system is one that matters. Okay, that is, power systems are normally designed. So the power systems are normally designed to be transiently stable with defined pre-fault contingency scenarios and post-fault system degradation. Okay, the power systems are normally designed to be transiently stable with defined pre-fault contingency scenarios and post-fault system degradation when subjected to a major disturbance. So for this reason, in most practical systems, the actual capacity of the transmission network is considerably higher than that at which they are normally used. So for this reason, in most practical systems, the actual capacity of transmission networks is considerably higher than that at which they are normally used. Okay, so the powerful capability of series compensation with sufficiently fast control to handle dynamic disturbances and increase the transient capacity of the post-fault or otherwise degraded systems can be effectively used to reduce the design underutilization of many power systems, reduced by the design underutilization of many power systems. So this is the transient stability improvement objective of series compensation. And now we are moving to third objective, that is power oscillation damping. The power oscillation damping. So in the controlled series compensation, can be applied effectively to damp power oscillations. Okay, the controlled series compensation can be applied effectively to damp power oscillations. So for power oscillation damping, it is necessary to vary the applied compensation so as to counteract the accelerating and decelerating swings of the distributed machines. Okay, so power oscillation damping, it is necessary to vary the applied compensation so as to counteract the accelerating and decelerating swings of the distributed machines. So that is, when the rotationally oscillating generator accelerates, okay, that is, when the rotationally oscillating generator accelerates and angle delta increases, that is d delta by dt is greater than 0, the electric power transmitted must be increased. Okay, the electric power transmitted must be increased to compensate for the excess mechanical input power. Okay, so when the rotationally oscillating generator accelerates and angle delta increases, that is d delta by dt is greater than 0, the electric power transmitted must be increased to compensate for the excess mechanical input power. And conversely, when the generator decelerates and angle delta decreases, there is d delta by dt is less than 0, the electric power transmitted must be decreased to balance the insufficient mechanical input power. Okay, insufficient mechanical input power to balance. So the required variation of the degree of series compensation, okay, the required variation of the degree of series compensation together with the corresponding variation of the transmission angle delta and transmitted power P versus time of an underdamped oscillating system are shown for an illustrative hypothetical case. Okay, here the required variation of the degree of series compensation, that is K, together with the corresponding variation of transmission angle delta and transmitted power P versus time of an underdamped oscillating system are shown for an illustrative hypothetical case in figure, that is 6.4. So I will show the diagram. So in the first diagram, there is the undamped system. So these waveforms illustrating power oscillation damping by controllable series compensation. First one is for the generator angle, and second one is for the transmitted power, and third one is for the series compensation. Third one is for the degree of series compensation, that is K. Okay, so the waveforms in figure 6.48 show the undamped and damped oscillations of angle delta around the steady state value delta naught. So this is the first diagram. So it is an undamped system. Okay, it consists of the waveforms with an undamped and damped oscillation of angle, that is delta, at steady state value delta naught. At steady state value delta naught. So delta naught. And next, the waveforms in figure, that is B, show the corresponding undamped and damped oscillations of the electric power. So previously, the first diagram shows the undamped and damped oscillation of angle delta corresponding around the steady state value delta naught, but the second figure shows the corresponding undamped and damped oscillations of the electric power P. So there is the second diagram P. Okay, P around the steady state value P naught. Previously we are using steady state value delta naught, and in this one we are using steady state value P naught. So following an assumed fault, that is sudden drop in P. Okay, following an assumed fault, that is sudden drop in P, that is this one. Okay, so fault that initiated the oscillation. So next one, the waveform C shows the applied variation of the degree of series capacitive compensation. Okay, so waveform C shows the applied variation of the degree of series capacitive compensation K. Applied, that is third one, this diagram. Okay, so as seen, K is maximum when d delta by dt is greater than 0, and it is 0 when d delta by dt is less than 0. Okay, K is maximum when d delta by dt is greater than 0, and minimum when d delta by dt is less than 0. So with maximum K, the effective line impedance is minimum, and consequently the electric power transmitted over the line is maximum. Okay, with maximum K, the effective line impedance is minimum, and consequently the electric power transmitted over the line is maximum. So when K is 0, that is d delta by dt is less than 0, the effective line impedance is maximum. The effective line impedance is maximum, and the power transmitted is minimum. So the illustration shows that K is controlled in a bang manner. Okay, the illustration shows that K is controlled in a bang manner. That is, output of the series compensator is varied between the minimum and maximum values. That is known as bang manner. So indeed, this type of control is the most effective for damping large oscillations. Indeed, this type of control is the most effective for damping large oscillations. So, however, damping relatively small power oscillations, particularly with a relatively large series capacitor compensator, continuous variation of K in sympathy with the generator angular or power may be a better alternative. So in this one, the damping relatively small power oscillation, particularly with a relatively large series compensator, and continuous variation of K in sympathy with generator angular power may be better alternative. So that is the explanation for the power oscillation damping. And next, coming to the last objective of the series compensation, that is subsynchronous oscillation damping. Okay, subsynchronous oscillation damping. So sustained oscillation below the fundamental system frequency can be caused by series capacitive compensation. Okay, sustained oscillation below the fundamental system frequency can be caused by series capacitive compensation. So the phenomenon referred to as subsynchronous resonance, that is SSR. Okay, The phenomenon referred to as subsynchronous resonance was observed as early as 1937. Okay, was observed as early as 1937, but it received serious attention only in the 1970s. Okay, after when it takes the serious attention means after two turbine generator shaft failures occurred at the Mojer generating station in southern Nevada. Okay, at that time we are taking this as the subsynchronous resonance concept. Okay, so after two turbine generator shaft failures, okay, at the generating station. So theoretical investigation showed that interaction between a series capacitor compensator transmission line oscillating at the natural resonance frequency, that is subharmonic frequency, and the mechanical system of a turbine generator set in torsional mechanical oscillation can result in negative damping with the consequent mutual reinforcement of the mechanical and electrical oscillations. So theoretical investigation showed that interaction between a series capacitor compensated transmission line oscillating at the natural resonance frequency and the mechanical system of a turbine generator set in torsional mechanical oscillation can result in negative damping with the consequent mutual reinforcement of the electrical and mechanical oscillations. So the phenomenon of subsynchronous resonance can be briefly described as follows. So the phenomenon of subsynchronous resonance can be briefly described as follows. So that a capacitor in series with the total circuit inductance of the transmission line, okay, capacitor in series with the total circuit inductance of the transmission line forms a series resonance circuit with the natural frequency of Fe, that is equal to 1 by 2 pi root LC, so that is equal to F into root of Xc by X. Okay, where Xc is the reactance of the series capacitor, okay, and X is the total reactance of the line at the fundamental power system frequency F. So since the degree of series compensation, that is K, is equal to Kc by X, is usually in the 25 to 75% range, the electrical resonance frequency T. Okay, next it is less than the power frequency F, that is Fe is the subharmonic frequency. Okay. So if the electrical circuit is brought into oscillation, okay, if the electrical circuit is brought into oscillation, that is by some network disturbance, then the subharmonic component of the line current results in a corresponding subharmonic field in the machine, which as it rotates backwards relative to the main field, produces an alternating torque on the rotor at the difference of frequency, that is F minus Fe. So in the electrical circuit is brought into oscillation, then the subharmonic component of the line current results in a corresponding subharmonic field in the machine, which as it rotates backwards relative to the main field, that is since Fe is less than F, produces an alternating torque on the rotor at the difference of frequency, that is F minus Fe. So if this difference frequency coincides with one of the torsional resonance of the turbine generator set, mechanical torsional oscillation is excited, which in turn further excites the electrical resonance. So this condition is defined as subsynchronous resonance. So the difference frequency coincides with the one of the torsional resonance of the turbine set. So turbine generator set, mechanical torsional oscillation is excited, which in turn further excites the electrical resonance. So this condition is defined as subsynchronous resonance. So large generators with multi-stage steam turbines. So large generators with multi-stage steam turbines which have multiple torsional modes with frequencies below the power frequency, so are most susceptible to subsynchronous resonance with series capacitor compensated transmission lines. So that is in order to able to fully exploit the functional capabilities of control series capacitive compensation for power flow control, transient stability improvement, and oscillation damping. It is imperative that the series compensator as a minimal requirement remains passive to or preferably actively mitigates subsynchronous resonance. So here, in order to be able to fully exploit the functional capabilities of the control series capacitive compensation for power flow control, transient stability improvement in polarization damping, it is imperative that the series compensator as a minimal requirement remains passive, that is non-participating to or preferably actively mitigate the subsynchronous resonance. So that means if you want to able to fully exploit the functional capabilities of the series capacitive compensation for power flow control, we don't use the polarization damping and the transient stability improvement. Rather than we are using this subsynchronous resonance. Okay. Next, so it will be seen later that power electronics based series compensators can meet this requirement either by their non-capacitive characteristics in the subharmonic frequency range of interest or by active control initiated damping action. So up to now we discussed about the objectives of series compensation. So in this class I am closing this objectives of series compensation, and in the next class I am going to discuss a few more concepts in the series capacitive compensation. Okay, thank you for watching this video.